Hey everybody, let's talk about section 4.2, polynomial functions and models. We're going to look at the correlation between the degree and, the general shape of a polynomial function. So let's get right to it. Okay, I actually added something like this to your D2L. You can have a gander at that, but let's go ahead and do a video about it. So first of all, let's see a motivating question here. How many turning points are there in the graph of a polynomial of degree 2? That is a quadratic, right? How many are there if the degree is 2? So we know the answer, okay? A polynomial of degree 2 is just a quadratic function. And ax squared plus bx plus c is the function. Of course, then there's one turning point. Exactly one turning point, which is called the vertex. Okay, so it could be, a local min, which is also absolute min, or a local max, which would also be a absolute max in this case. That has to do with whether the leading coefficient is positive or negative. And this, we'll see later, has to do with the end behavior of the polynomial function. Okay, and so the question is then, what's the deal with that in general? Well, the general fact is that if f of x is a polynomial function of degree n, then the maximum number of turning points is one less than that degree. So the maximum number of turning points is n minus 1. We see that in the case when n is 1, or a linear function, and there are no turning points. We see that when n is 2, when it's a parabola and there's exactly 1. So we see this. When n is 1, we have a linear function, there are no turning points. When n is 2, we see there's exactly 1. Well, one turning point. There's the right S there. Okay. However, if you get higher order or higher degree, right, then you could have number of turning points is no greater than the degree minus 1. Okay. You could have fewer than that. So for instance, here's a cubic function perhaps with 2 turning points. Here's one that doesn't have any. Okay. So there's a theorem that says that if you have an odd degree, the number of turning points that you could have, or the number of local max or min, is at most one less than that degree, but then it has to be, an even number less than that if it is less. So for instance, if n is 3, you can have either 2 or 0, but you can't have one turning point if the degree is 3. And the reason for that is because of this n behavior I was talking about. So what happens to the function as x gets really big or really small, so way to the left and way to the right, if the degree is odd or even, that determines what is possible for where those things are going. Okay, so when else is this important? Well, say we wanted to model some data. So for instance, say we wanted to find a polynomial function that models some data. So find a polynomial function of minimum degree, and that minimum degree thing's kind of important, that models the data. Okay, so I'm just going to pick some numbers here at random. X, say 0, then 1, then 3, then 5, then 10, then 12. It starts out at negative 10 for the y, then up to 6, then down to 0, then down to negative 3, then up to 11, and then up to 17. Okay. And what I was sort of describing as I was going there was what we need to do to figure out how many turning points there are in the data, and then that tells us the number of turning points that we can have in our polynomial that models the data. That tells us what the minimum degree has to be. Okay, so if we look at consecutive data points, right, the x values are going up every time. So if we did the average rate of change between the consecutive data points, we would get, rise over run. The rise here would be positive, right, because we go from negative 10 up to 6, but of course the run is always positive because we're going from left to right. So here, the polynomial function that would model these data would most likely be increasing. Okay, but then look, we go from negative 10 up to 6, and then we go from 6 down to 0. So that means we have a turning point here in the data. So we want to have a turning point in our function as well. We're still going down, right, from 6 to 0, then 0 to negative 3. That's still negative average rate of change. But then we're going to pop back up and go up to 11. So now we have another turning point. And then we're still going up, so we get 2 turning points in the data. So we're going to have 2 turning points in our model. So 2 turning points in the data means the minimum degree that we want to use is 3. Okay? So when we try that, we're going to use, so we need cubic regression, cubic reg. And let's take a look at how to do it. All right, so let's go to our calculator. We go to Stat, Edit. We have old data in the list. We're going to clear it out. I did a similar thing earlier, but I cleared it out, and we're going to redo it. Okay, so let's get back our data points here. Okay, so 0, 0, 1, 3, 5, 10, and 12. Okay, so I did that with my 10 key here, so I typed it in. Negative 10, 6, 0, negative 3, 11, 17. Most common mistake with this is just typing in wrong and getting the wrong degree. Okay. So how do you get cubic regression? Then you go to Stat, Calc, 6, cubic reg. Enter, 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 enter. And notice I've got r squared here. If you don't have this, then you have to go to second 0, or the catalog, and look for diagnostic on. You remember we did that a long time ago. Okay, so the answer here is a cubic polynomial. We get f of x. So cubic reg, once again, this is stat over to calc number 6. Okay, here f of x is roughly 0.047x cubed minus 0.683x squared plus 3.404x, and then minus 4.805. Okay, the r squared thing is about 0.74. That's not that close to 1, but it is, decent. So this is not the best of models. If this were a really good model for the data we're given, then this value would be closer to 1 perhaps, but in real life you don't often get much better than that. Okay, now I don't know if you've noticed, but in our daily lives these days, we've seen a lot of and heard a lot of talk about projections and modeling. As you know, this is Intro to Math Modeling class. We see that modeling, the growth or average rate of change of infection rates with COVID-19 has been a big deal. So just in case you were wondering when you're ever going to see this stuff, well, you will, because we do. All right, the last thing I want to talk about here for this video is called end behavior. Note that there's also a correlation between the number of x-intercepts that a polynomial function can have, and its degree, but I'm going to let you read that. Essentially, the maximum number of x-intercepts you can have is equal to the degree. Just like the maximum number of x-intercepts you can have for a quadratic function is 2, right? You can have as many as 2 real solutions to a quadratic equation. Same is true for any degree, right? You can have 3 if the degree is 3, but no more than that. All right. Now, the end behavior is what happens when, so this is what the graph looks like. The graph is roughly like the graph of just the leading term as x goes really, really far to the right or really, really far to the left. So if x is really, really big, then the graph of a polynomial function, right, say f of x is a sub n, x to the n, plus a sub n minus 1 x to the n minus 1, and so on. As x gets really, really big, all the terms that are not this first term, they stop mattering very much. Okay, so if x is really, really big or really, really small, these things right here are useless in terms of determining the shape of the graph. So we're going to look at the 4 cases that are involved in an end behavior, and they have only to do with that what the trend of the leading term would be. So the 4 cases are these. You have leading coefficient is positive, and the degree is even. You can have the leading coefficient is negative and the degree is even. Or you could have leading coefficient is positive, the degree is odd. I don't know why I did it in that order, but that's the way it goes. Okay, so basically they mirror what happens in the case when n is 2 or n is 1. We know all about those. So if the leading coefficient is positive and the degree is even, the shape of the graph is very similar to the shape of a parabola that opens up. Or vice versa, if it is negative leading coefficient, it should go down on both sides. So in my math lab, it'll say it rises to the left and right, or falls to the left and right. Okay. For instance, here, if we were in class, I would probably say this is like touchdown symbol, right? Someday we'll have guys do touchdown symbols again. It's a little, social distancing joke there. Not really a good joke. But more or less, if the leading coefficient is positive and the degree is even, it behaves like a parabola opening up. If the leading coefficient is positive but the degree is odd, then it's like a line that's increasing. Okay? If the degree is odd, so that's like n equals 1, right? N is 1 is odd. Vice versa if the leading coefficient is negative. Now, in between these dotted lines, the graph could be really, really crazy. It could go up and down a bunch of times. You know the number of turning points. But way to the right, way to the left, this is what's going to happen, just depending on the leading term, leading coefficient and degree. Oops. So if I were in class, I would tell you that this case here, the leading coefficient positive, degree is odd, is similar to a John Travolta disco dancing move. There he is. So it's like disco for righties. Dun 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 dun. Shouldn't do too much of that, or I'll get into copyright infringement. Anyway, can you tell by the way I use my rock? I'm a woman's man. All right. So anyway, I think I'll end there. If you have any questions, put them in the appropriate places. Okay. So, let me just show you. Actually, before we get there, let me show you on the calculator what you might see. So here I've got a cubic function, right? And the leading coefficient is 1, right? So that's positive, and the degree is odd, so it's disco for righties. Right? Falls to the left and rises to the right. If we had instead degree 4, Now it would be touchdown, right? So let's look. I think if I do the standard window, this one might show me what I would need to see. Okay, there it goes. Another thing that's nice is we know that this